I'm ready to start. Welcome everybody. My name is Stefan Dirnsdorfer, and today I'll be talking about image processing in the context of test automation and testing and automation. My talk will be mainly based on these articles in case you want to read more. Professionally, I serve as a CTO and co-founder of a company that brings TestUp.io, an image-based test automation service. Okay, let's get started. Imagine you want to test an application on a phone. You want to initiate some actions automatically and check if the resulting states are correct. Image-based algorithms haven't been powerful for all that long, so traditionally you would rely on some internal states like a component tree or a DOM. Developers like this kind of representation because that matches their internal model. That's how they organize the modules, how they place folders, and how they design object hierarchies. However, there might be multiple reasons why you don't have access to these internals. The development could be outsourced, you could be heavily integrating with third-party components, or, to say it more bluntly, you might be vibe coding. And if you're vibe coding, then you're not testing, and you could say, well, I'm vibe coding, then I might as well do vibe testing. But when your vibe test fails, you will see some gibberish like this, which you cannot interpret. So of course you can then do vibe fixing, but you neither understand the test nor the code, and it will not be very good. Wouldn't it be better if you got a graphical representation of what is the intended accepted state and the state of the current version? The problem is that even for humans, it takes a while until you spot the difference, and once you discovered it, it pops out to you as a major flaw. The ideal world would be if an AI helps you flagging that change and attribute it to an intended, an acceptable, or a faulty state. So that is the content of my talk for the remaining 47 minutes. And we will see where AI stands today, how fast it is moving, where it will be tomorrow, and what it can and cannot reach. After all, we need to consider that with regards to visual tasks, even we humans cannot solve every problem. When we look into the world, we are permanently susceptible to various optical illusions. And we have these illusions not because we are on LSD somehow, we have them because evolution had to make compromises in order to give us some visual capabilities at the expense of others. But we are not here to solve all types of visual tasks. We are here to solve the problem of some quirky UIs on front ends that either are on devices that we do not fully understand, or we have systems that are intentionally obfuscated, or are just by nature so obscure that you just don't want to know anything about their internals. Let's get more practical with this example. So the test script is here 3 steps. I want to open an app identified by a picture, then I want to find an item identified by the name Munich, and then I want to check if the represented graphics matches my expectation. To run this test, I chose Cloud Sonnet 4.5, the computer use tool. That's not what you get when you open the desktop or the chatbot, that's a specialized API. The latest version just came out 2 weeks ago, so I updated my presentation already to reflect the latest behavior. But the first beta came out with 3.5 well over a year ago. So this is very new, and I will point out to you when some changes happened in the past year. So as always, we start with our initial prompt. So we send over the prompt together with the picture to the server. And sure enough, it waits for some time and comes back with a response. As usual, it has the explanation of what it is thinking, but additionally has a technical component where it says how it wants the computer to be used. In this case, it wants to get the screenshots, a request that is easy to fulfill. I send it over, and again, the AI takes some time thinking and comes up with a new response. This time, it discovers that it found, or it confirms that it found the requested icons identified by the street logo 280. And in addition, it has the computer use instruction showing us where to click. In case you're wondering why this is a click and not a tap, this is because the AI is not using an iPhone, it is using a simulated phone which is accessed through a web interface that I manipulated to create some interesting scenarios. Now that we've understood how the interaction between our software and the AI works, we can have a look at how this behavior works out over time. We click as instructed and wait for the screen. I send the same screen over again to the AI, and the AI says, oh, nothing has changed, let's wait. In the technical body, it even says it has to wait for 2 seconds. I find this even quite remarkable that the AI has an understanding for that nothing happened and for how long it makes sense to wait. I mean, this has happened to you, I guess, very often, that you clicked on the phone and nothing happens. Humans solve this problem quite naturally, sometimes without even noticing. But for traditional automation services, this is a major hurdle and often breaks down the entire process. So, after some time, I sent over the same screen again. And I realized that nothing happened, even after the wait time. Now, the old version would repeat in a loop, but that would be boring for you, and the new version doesn't do this anymore. The new version finds out a new way to modify it, maybe click a slightly different place on the screen. So it does the change click, and voila, the Maps application is opened, and the Claude Sonnet confirms this, and we have solved our first step. Well done. Let's move on to the next item. We want to find Munich. Here we have to solve a number of intermediate screen problems that we need to click through. Traditional automation would be completely confused if something like this happens, but the AI sees, okay, just continue. The AI figures out that we don't need to share our location. Very clever, very privacy oriented. And finally, AI has to disable notifications. Even AI knows that they are annoying. After that, a search interaction item occurs. The AI clicks on it, types the search term, and then correctly identifies the search result, not being confused by all the advertising items displayed next to it. I find this quite clever, and certainly the second task also has been done by the AI. Now the third step, we need to find if the correct map is shown on the screen. So I ask Claude Sonnet, is this the screen that we want? Yes, it is. Perfect, isn't it? So this is what we wanted. We wanted a simple instruction, run the test, and do the checks. That's fine. Now maybe I should finish my talk early, because that's what we wanted to do. Or we have a second closer look. Let's first look at the icon. The icon that we requested had a 280 road symbol in it, and the icon that it found didn't. You might say, well, that's pretty clever. It realized that this is the same app essentially, but if we remember, in its thinking, it confirmed to us explicitly that it found the 280 road sign. Was it hallucinating, or what's going on here? Well, maybe let's give it the benefit of the doubt. Let's review a second thing. Let's review the map. The map that I expected to show had all the roads connected. The road that the manipulated phone did show had all the roads cut. Well, this is a major flaw. If you rely on that road for navigation, you might be concluding that Extinction Rebellion had taken over the city center. How can this super intelligent clanker miss this apocalyptic scenario? There is something wrong. So for testing purposes, we have a problem because it's not very reliable. But let's first review what we have done so far. We have looked at visual UI agents or visual computer use agents. They are very strong because they can operate all types of devices. They are very resilient against kind of modified behaviors, and they're easy to instruct in human language. Problem is sensitivity. That's something that we need to explore now, and of course, as always, the AI models are a bit more resource hungry than traditional methods. This is a slide that I took from the Computer Use Model Survey. This is version 8, released in May this year. So it doesn't have the latest Sonnet model yet, but we will see that there's an abundance of models lining up, starting at around 2023. So that's when they became like usable. On the top right, you see OpenAI and Gemini's operator models. They are similar, but more focused on web use, which has an advantage that you additionally have access to the web source code and the DOM. There is one model I want to discuss with you in more detail because it's an open source model and we can learn from it how do these things work internally. The DAT-ACT model is the model that I want to show you, but the group doing the DAT-ACT model also releases a training set, the OmniAct set. This will give you some insight on how the systems are trained. Here, look at this example. Here, the AI needs to understand what a stock price change is. It needs to figure out where it has to swipe over in order to get the result. So if you're reading about success rates of 40%, we are really dealing with requests that are on this level, which take a very deep insight, or here where you need to hover and scroll until you get to the right value. So in terms of interaction planning, they are already very, very good. And for us testers, we can describe the steps in more detail, and they will be perfect. But how do they work? The DAT-ACT model team shared these slides. And it works like this. The screen comes in and will then be analyzed by different specialized models. One, for example, doing object character recognition, extracting all the texts. One will be trained to extract all kind of known logos. And another model will extract certain unnameable things identified by colors or basic shapes. Now, all these findings, together with their coordinates, are stuck into a traditional language model, which could be ChatGPT. And here we can already see that as long as the visual display can be described in human language easily, the model will be able to infer the right results. But if something gets a bit more confusing and murky, the textual representation is not enough to solve the task. Let's look at a few examples of where this UI model breaks. This is back to Claude Sonnet. I gave it 2 screens and asked it, where is the difference? In this case, it correctly identifies these are 2 different versions of the same maps application. Even if you ask it again, knows at what year the style change happened. So Apple did a good job infiltrating the publicly available training data with its marketing speak. Let's look at this example. Here, the AI does not find a difference, and that is because this movement wasn't described in text. Of course, the numbers must have been different, otherwise it wouldn't have been able to click on it. But since bounding boxes are not really unique, it must have some tolerance before it rejects this as different. So here, it did not verbalize, at least, it did not explain that this is a different screen. What about this one? As soon as 2 icons create a new relationship, here an overlap, this overlap is verbalized again and can be found in the text. Going back to the map, you can now easily understand why it's not feasible to describe in human language what the road connections are. we would have to take a huge amount of context and huge amount of text, spoiling all the reasonable and realistic scenarios that you want to do with it. So obviously, the generative AI does not do it here. But this doesn't look like a very complicated task. It's now time to do some real image processing coding. Now is the time where we can toss aside the generative AI and prove that all the years that we've spent honing our coding skills were not in vain. Okay, I'm joking, of course. We use GPT-5. GPT-5, almighty intelligence overlord, please compare these two images and see how it does. Now, for the first half a minute, it creates all kind of computer code analyzing these images. It implemented 3 different algorithms and flagged all the differences. Now, there's one thing I didn't tell you yet. This map, apart from having the roads cut, also was moved by 1 pixel. This is a layout change that happens. If you are in front-end development, you will know that layout changes on that level happen all the time with the new browser version coming out, the new operating system, and new screen resolutions. These kind of errors are happening from version to version inadvertently. And GPT-4 would have stopped at this point and said, these pictures are equal. So why would it conclude that the pictures are equal? Obviously, in its training data, it had many similar confusing situations where the label, the equality label, was set to true. And of course, you could prompt it to see the cuts, but then the problem is it's just not sure. Whatever you want it to say, it says. It doesn't know. But we are now with GPT-5, and GPT-5 continues. Oh, how lovely. It does a fast Fourier transformation and computes a phase correlation. It figures out that the images were moved by 1 pixel. It only needs to undo this movement and then can compare the pixels. See how it does? Sure enough, it makes the algorithm, comes out with the exact map of where the pixels are missed. Now it needs only to derive what this is at this point, and no street or routing changes. It was not able to name and correctly identify it. But progress is remarkable, and I see likely that GPT-6 will be able to name that. But keep in mind that we just had a uniform translation of 1 pixel. With a phase correlation, you wouldn't even be able to detect the slightest amount of scaling or a non-uniform transformation where roads and text may be moved differently. So now we can really toss aside the generative AI and see how we're working. But we are halfway in, don't worry. If you have this problem in practice, you will know by the end of this talk how to solve this. Let's first make some research. What is out there? If you are in front-end testing, I know, are some of you, who is in front-end testing of you? Okay, yeah, you're at the right place. You're probably using Playwright or Cypress. These 2 platforms are the market leaders, and they have the capability to compare images. Internally, they both rely on the very same library. It's called Pixel Match. And Pixel Match relies on an algorithm published in 2010, which doesn't seem like that old. No, it is old. It is very old. And it does what it promises. It compares pixels. Let's review the problem with the pixel movement. As long as the images are perfectly aligned, you can compare the image pixel by pixel and see where it fails. But as soon as the images are not perfectly aligned, differences pop up everywhere. And these alignment changes, the position changes, happen all the time, and you don't hardly have control over it because it happens from version to version. Let's look at this more extreme example. Here I have 2 versions of a map, and it changed in 2 ways. First, it was rotated, and second, roads were cut. And if you're not able to separate those 2 effects, that means that maybe one of those two changes is intentional and the other one is just acceptable, then you will be blinded. You will not see the one effect because the other destroys your entire view. So the challenge that we have for the test automation is to separate these two effects from each other. And I tested a number of libraries, and of course, this was not solved, but there is one library that stood out as a bit more capable than others, and that is the applitools. The applitools was able to detect displacements of 2 pixels roughly, yes, 1 to 3 pixels depending on context. And the first question that I have is, how does applitools do it, and how can we scale that method to more complicated scenarios? And I was, here you can see how it flags it, how it flags the changes, and I was able to replicate these performance with a simple convolutional neural network. And this is the setup. So basically, I use a small sliding window of size 9 by 9. And the training data, you see 4 examples of training data. Some of them are labeled as equal, and some of them are labeled as false. And this window can slide over the image and pick out changes with tolerance to some pixels of difference. And I was using about 30,000 weights and 8 layers. So this is a very simple model. And by the standards of 2015, when they started, by their standards, this was intelligence. This was artificial intelligence back then. But now we would call it just machine learning or statistics. Anyway, this one works, and that's what they are doing. Yes, and this is also what I described in the InfoQ article in case you want to know the details about this procedure. Now, let's focus on the actual challenge at hand. So we have one image that is the correct version, and one might be the incorrect version, and we want to spot the differences. This is actually a game that we played as children all the time, and we were quite efficient at doing this, even if one of those pictures was somehow distorted. And that's because we are used to seeing things from an angle anyways, and we are not disturbed by a slight distortion like this. This doesn't hamper our performance. But for AI, this task, that's exactly the testing task, is very hard. And it's not only hard because there are so many details, it's also hard because some of those things are really hard to describe. Look at these clocks, for example. The clock bench AI benchmark measures human performance at reading analog clocks at 90%, whereas the best AI models barely reached, and didn't even reach 40 yet. So reading a clock is already very difficult. And that's just not to mention all the other details that you find here. But for a laugh, let's give it to ChatGPT anyways. Dear ChatGPT, please compare these 2 images. Now, they are from Wikipedia's Spot the Difference page, and GPT definitely had this picture in its training set. And sure enough, it found the clocks, but incorrectly labeled their times at 3 o'clock and 4 o'clock. And it found other things like strawberries. It found 5 and 4 strawberries, and maybe I missed them, so let's ask GPT. Please show me the strawberries, and here we go, it made a nice picture. Let's be fair, this is better than what I would have drawn off the top of my head. But, okay, let's look at the clock. The clock is not equal. They're not circled, and they are definitely not showing 3 and 4 o'clock. And why does the kid suddenly have 2 heads? Or is it 2 kids now? Anyway, this is weird. So what do we do? Let's first review what is the difference between humans and computers to understand what's going on. For this, let's have a look at the vision pipeline. First, we start with the raw illumination signal. Then we extract some features. And finally, we have some idea, some conceptualization of what we are seeing. For computers, these layers are, on the starting level, the bitmap, the pixel data. On the next layer, we have the convolutional neural networks with more and more features as the layers get higher and higher. And finally, we have the embedding, which we get with the latest attention models. So that's how the computer processes our images. But how does a human do it? Well, on first sight, the human works very similar. It has raw data captured by the retina. Then it has some feature detection algorithm, I wanted to say, feature detection mechanisms in the thalamus, or to be more precise, the lateral geniculate nucleus. That's where the features are detected and then get forwarded to the visual cortex and our frontal cortex. Now, where is the difference between the computer and the human? The interesting or surprising finding is that there are 10 times more neurons leading from the cortex, from the frontal cortex, into the visual system than the other way around. That's as if you connected a camera to the computer and there was 10 times more data flowing from your computer into the camera than is coming out of the camera. And that is because we do not actively, the vision system does not inform us what it sees. It's more the other way around. Our visual cortex makes hypotheses of what could be there, and the vision system's task is more to confirm whether that is there or not. So one interesting study that I found very telling of this effect is that they gave hallucinogenic drugs to mice. And you would expect they have hallucinations and the visual system goes all wild and makes up things, but the finding was that actually the neurons turn dark. And that is because the hypotheses were just randomly confirmed as, oh yes, that monster is there, without even checking. So the visual system actually checks hypotheses and does not inform us of what is there. And you can observe yourself if you play such a spot the difference game. You can see that your eyes move left and right. You consciously find corresponding spots. You formulate hypotheses even with your verbal system, and you think, oh, is that mountain really shifted from left to right? And then you confirm this hypothesis. So this is a multi-step chain of thought reasoning that we humans naturally do, but that's not what AI is doing with a simple forward-oriented method. So how do we go on and find the differences on these images with the computer? Okay. What we need to do first, we need to squeeze the images such they match up, that they line up with each other. And this process is called a registration. Registration is a term that was first coined by cartographers. When they had maps from different regions, they had to line up the landmarks and find how these maps go together. Nowadays, image registration is used in multiple disciplines. For example, the self-driving cars, they need to know how things flow from one image to the other, which is also known as optical flow tasks. Stereo vision has this problem, and medicine has this problem. If you, for example, want to observe the development of a potential tumor, then you have a sequence of images in which the organ moves over time in the body, and at the same time, the metastasis develops. So you need to undo a larger transformation to find the changes in the embedding content. So, how can we solve image registration? Let's go backwards in time in 2003. That's the algorithm that you find in OpenCV library, a widespread computer vision library. And it uses this Farnback algorithm, and you see that, well, it's kind of doing the thing, but it's not there yet. Fast forward to 2008. Now the flow looks a bit cleaner, but still has a lot of mistakes. And then go back to now, 2020 more or less. Now this problem is perfectly solved. The question is no longer if we can solve this registration, but more what exactly do we define as the boundary between a registration and an actual change. So you find on Hugging Face, for example, you find a huge number of models specialized on astronomy, on navigation, on medicine, so you have to choose your algorithm. But once you have chosen one, you can align these two images and then use the algorithm that we have discussed before to flag all the changes. Now what is missing, of course, is to name them. And we can make clusters and give it to the AI one by one and ask it what is there. But that's the part where we still have, I guess, a few years to go before we can have reasonable textual extractions of what the change is. So let me summarize what we have seen so far. We have discussed that for testing applications on a graphical device, we have a traditional way of using it, and that is explaining it in terms of its internal data structure, component trees and DOMs, which probably most of you, or most of you who are testing front ends are aware of. But we have seen that in the recent years, there is more and more powerful algorithmic methods available to solve this task graphically, especially with the UI agents starting to become usable in like last year more or less. We can now operate with these devices without relying on any structure. Then we have seen that for testing purpose, for quality control, these generative AI models are not very powerful and are easily confused, especially when the shown items are graphically or have a rich graphical content, but are not easily described in human language. So here the system has major weaknesses, and we must rely on maybe more explicit algorithms. One of the algorithms that you will always come across when you do this is the image registration. I don't know why none of the software packages, Cypress or Playwright, have this as part of their tooling, but the image registration is the first thing that you need to do to compare to images. And once you have the images registered, you can then use these traditional algorithms to compare them. So this is also the topic of the publications that I made prior to this talk. This also concludes my presentation. This is my LinkedIn. You're happy to connect. And also don't forget to check out our image-based test automation service that you can find online.